Hey, greetings, Wildcats. So I'm gonna do a couple of review videos based on what we'd already covered in class, and then maybe I'll continue with this. So this video is gonna cover finding the marginal cost. This is something we did last Monday and Wednesday in class. Okay, so if you were actually in class on Monday and Wednesday, you probably already heard this. So I'll provide it, particularly for those of you who had other pressing issues that took you away from class, and it may be a useful review for those of you who were actually there. Okay, so in finance, we worked with primarily linear cost functions. So we started with the idea that we would have some amount of fixed cost, right? We always draw this kind of dotted line, called it fixed cost. And then we said, all right, you add on top of the fixed cost, you add the variable cost. So this wedge between here was the variable cost, and then we got our total cost, right? And so we typically dealt with this kind of format, and the equation for this, so this would be um, uh, uh, total cost and quantity, right? And so the equation for this would be something like total cost is equal to, say, 100 plus 10Q, right? And then we would say, okay, the slope of this curve is 10, right? Sorry, slope of the line is 10. Um, and so we did this a little bit. I said, well, what is the marginal cost for this production or cost function? And marginal cost asks, really, if you remember, right, marginal refers to one more. So what is the cost of making one more unit? So if we plug in, say, TC of 1, so what is the total cost of doing 1? We would have 100 plus 10 times 1 would be 100 plus 10, or 110. The total cost at 2 would be 100, right? Because this is your fixed cost. This is your variable cost. Would be 10 times 2, or 120, right? So the marginal cost is the cost of doing one more. So the cost of going from 1 to 2 is 110 to 120. So 120 minus 110 is 10. So the additional cost of making one more unit was um, was 10, right? And then if we go to 3, its fixed cost is still 100 plus 10, right? Times 3 now is 130. And so marginal cost of going from 2 to 3 is going to be 130 minus 120, or 10 again, right? So why is it always 10? Well, because every time we add one more unit, we're adding $10 more worth of variable cost, but our fixed costs stay constant, right? This is fixed, that's variable, right? And so this is that is a property of a linear cost function. Wherever you are on the curve, right, whether you're going from 1 to 2, or from 200 to 201, the additional cost, or the marginal cost, is always going to be $10, right, for this particular function, because the variable cost is just 10Q. All right. So if you wanted to find the marginal cost of a linear cost function, you are just looking for the slope uh, of the um, of the function, right? So if we said, all right, let me just write that back down here, 100 plus 10Q, right? That falls into the same your basic slope intercept format of y equals b plus mx, right? Where m is the slope. So you can really just kind of eyeball this equation and say, oh yeah, the slope is 10, right? Because it's the constant that's associated with the variable that's on the x-axis. So in this case, q is the x-axis, so the slope is always going to be 10. Another quick example, right? If we said TC equals 450,000, right? That's our fixed cost, plus 500Q, so just a bigger number. What would our graph look like? Well, we'd have, right, same thing. We'd have 450K, right? And that's our fixed costs. And then we would have a line starting at 450,000 and going up to the right with a slope of 500, right? Because y equals b plus mx, right? Where 500 is my m, q is my uh, uh, x-axis here, tc is my y, right? My y is my vertical axis. Now, this is my total cost, my fixed cost, and again, my total, I should say total variable cost, right? So the slope, we can just eyeball it. It's right there. And if we did, went through the process of being, all right, if I do, what's the total cost for one? What's the total cost for two? We're going to find out that the marginal cost for this function is just the slope of 500. So if I asked you, looking at this function, if I said, what's the marginal cost? You would just ignore the 450,000. You would drop the Q and you would just say MC equals 500, right? So, so marginal cost, again, is always the cost of doing one more thing, right? One more unit. And that's for a simple linear function. But the reality is that most cost functions in the real world don't have true or constant linear properties. Instead, they have some element of exponential acceleration, right? So what do I mean by that? Well, this is a linear function because it has a constant slope. So it's a straight line. When I draw this, I would use it, if I really wanted to make it precise, I would use a ruler and I would just go zip right up here and it would always look the same. A cost function that has has accelerating properties is going to be an exponential function, and it might look something like, hey, here's my 450k, and I might go, initially might start to look like the one up here, but as I go out, it tends to go up at an accelerating rate. So it might initially have a slope of 500 or something close to 500, but as we move along the q-axis, right, the total cost accelerates, so the marginal cost is increasing, right? So from going from, say 1 to 2 down here is a relatively small marginal cost, right? We go from this to this, right? Small. And if this was, say, 10 and this was 11, I have a fairly large gap here. And let's say this is 11 and this is 12, right? I have an even bigger gap. So this is the marginal cost going from 10 to 11. This is the marginal cost going from 11 to 12. And you can see that that gap is getting bigger as we move along, right? And if I kept going up, right, the next one might be like way up here, right? And now I'm crossing over to that other graph and it's looking kind of messy, but you can get the idea that that marginal cost is going to go from pretty tiny down here, right? So close that I can't really draw it with this blunt marker, to out here a little farther out, it's kind of gotten a lot bigger. And then just one more, right? And it got like at least 2, maybe 3 times as big as the prior one. So in this example, the marginal cost is going up as I move out. So it's not a linear function. Instead, this is an exponential function. And so what might whereas this function had that nice neat 450,000 plus 500q, this one might look a lot like that, right? So that would have been the equation for that line. This line might have very similar start of the equation, right? It might have 450,000 plus 500q, but then it might have a kind of what I like to call a kicker, which says, say 1/10 q squared, right? So this 1/10 q squared is going to add on a little bit every time that we add one more to the, as we add one more Q, this number is going to get bigger. Now, the thing about this number, because it's a squared number, it's going to get bigger at an exponential rate, right? And that shape is called a parabola, right? So if we draw that, when you were doing, eighth grade math, right, you would draw a parabola and it had a shape like this. Because we're only dealing with the positive side of the x-axis, we're only going to see that upward curve. If we had negative q's, we'd go over here, but negative q's are nonsensical. So we don't have to worry about the left side. We're only interested in the right side of the parabola. So this is exponential growth over here in the shape of half of the parabola. So the problem here is, how do you find the slope of something like this, right? Because the marginal cost is still equal to the slope, right? The marginal cost is still equal to the slope. It's the amount, the additional amount that I get from doing one more. Well, we get that from calculating the slope of the curve. So if my curve now looks like this, right? Where's my slope, right? Because it was really obvious when I had this nice straight line, the slope is just, how much it goes up by, but it's going up by, some small amount over here and over here by a whole large amount. How do I know what the slope is? Well, the nice thing is we have a relatively straightforward tool, and it involves calculus, and it's just simply taking a derivative. Now, I didn't tell people when I taught it in class that we were doing calculus because I didn't want people to get anxious about it, but it's really, really simple. Okay, it is a mechanical process. Now, here's the thing, and this is the dirty secret of calculus 1. You spend, like, if your calculus class is like 14 weeks long, you spend like the first 8 weeks learning all this math that goes behind this process that I'm going to demonstrate to you. And then, like, you come in the next class after you've like gone through all these limits and stuff, and then the teacher's like, here, and now we could just do this shortcut, and you don't have to do any of the rest of that, all that work that we've just spent the last 8 weeks proving actually works, right? So I'm going to just skip the first 8 weeks of calculus for you and do this relatively simple procedure that allows you to calculate the slope of a curved line, right? So let's jump back to our initial curve cost function that we were using. We're going to use a smaller number, 100 plus 10q, right? That would be our straight line here with fixed cost of 100, variable cost of 10q, right? And we'd have a nice straight line. But let's add a kicker, right, to this one, and we'll just do something like, 1/100th q squared. Okay, so now we wind up with this parabola, half parabola here, exponential growth of our total costs. Okay, so we can't say just by eyeballing this what the marginal cost is, at least without our technique. So what we really want to know is, or the way that we say what the slope of this curve is we take the tangent at different points on the curve, and that tangent tells us at any given point the tangent is the slope, right? So we want to find out what the tangent is. And what is the tangent? The tangent is a straight line that can be drawn that touches the curve at any given point, right? So a point here, I want a straight line that touches the curve only at one point. So the tangent is, I bring my straight line in from the side, and I bring it in and bring it in and bring it in, and as it just touches, it's going to touch at one point, because that curve, right, is going to touch at one point. I can keep going, right, and then now I've got a line that that touches the curve at 2 points, right? It touches down here and it touches up here, but that's not what I'm looking for. what I'm looking for is the line that just barely touches here. And you can see that one would be like kind of like that. And if I brought my pen in from this side and I approached this point, it would be just about right there, right? And that slope would be different than this slope, right? This one has, the slope of this line is very steep. The slope of this line is pretty close to 1, right? And then the slope of this one, when I come in at the bottom, is going to be fairly flat. Just like this one is very steep, this one is going to be very flat. So at any given point on this line, I can bring my straight line in and find, a point that just touches it. And you can see as we move along the curve, it's the tangent line starts out relatively flat, and then it gets steeper and steeper as the line accelerates up, right? And so the slopes of these tangent points become the marginal cost, right? So the marginal cost is still equal to the slope, but the slope is not as easily calculated, or it's really, it's not quite as simple. It's not just, you can't just eyeball it. You have to have some means of figuring out what's the slope of the tangent at each of these points, okay? So now I'm gonna give you the trick, okay? So for this function, the marginal cost, now remember, we looked down here and we said, looked at this line, and this one was TC equals 100 plus 10Q, right? And we just looked at that and we said, oh, it's going to be 10 because that's the rate at which this line increased. When you said 10, you just were like, yeah, I can just ignore the 100. You're not telling me anything about the 100. You're just focused on the slope. Well, up here, we're also just focused on the slope. So we're going to ignore the 100, okay? So the rule, the technique here is, as I look at a function, if the first term, right, this here, is just a constant, then it goes to 0. We just ignore it. Basically, we just set it to 0. Just like down here, I say, well, what's the marginal cost? You don't say anything about the 100. You just look at the slope of the line. So up here, again, if I'm looking for the slope of this line, you don't care about how high up it is, whether the line started up here or was down here, right? You're just interested in the slope of that line. So this has nothing to do with the slope of that. So we're going to set this term equal to 0. Then we're going to start with a little bit of magic, okay? So the magic goes something like this. That Q, right, is actually has an exponent, and that exponent is Q to the 1. And say, well, Q to the 1 actually is just Q. So why am I writing the 1? Well, I'm going to write the 1 in there to make my life a little bit easier, okay? So when you're new at this, it's useful to write the 1 in just to kind of help yourself remember what's going on. So I'm going to jot the 1 down. So that's the first thing I'm going to do. I'm going to ignore, or you can even X out any constant, whether that's 100, right? Or our other example, we had 450,000, right? Just X that bad boy out and set it equal to 0. Now, I'm going to look at my 10Q to the 1 now, and I'm going to take that 1 and I'm going to bring it down, right? And then I'm going to bring down the constant that's associated with my variable, in this case, 10. So now I've got 1 times 10. Then I'm going to bring down my Q, my variable in this case, right? It could be any variable. It could be Z to the 1, right? And I'm going to bring down the current exponent, which is 1. And then I'm going to subtract 1 from it. Okay? So I've got now 1 times 10 times Q to the 1 minus 1. Well, what is 1 minus 1? It's just 0. So let me write a fresh line down here. I've got 0, so I can ignore that. 1 times 10 is 10. And then I have Q to the 1 minus 1, which is Q to the 0, right? Well, what is Q to the 0? Q to the 0 is 1. So my Q to the 0 becomes 1. So I don't have to write a Q down here. So really I've got just 10. All right. Now I'm going to do the same thing with this one, right? So a minute ago, I brought down the 1, right, the exponent. Well, in this case, I've got an exponent of 2. So I'm going to bring down a 2. Then I'm going to bring down the constant that's associated, right? So that's 1 over 100. Then I'm going to bring down the q to the 2. So I'm going to bring down this whole thing, and I'm going to subtract 1, just like I did over here. Okay, so let's bring this down a scratch. So 2 times 1/100th is 2 over 100. 2 over 100 is 1 over 50. And then q to the 2 minus 1 is, 2 minus 1 is 1, right? So q to the 1 is just q. So now I've got 1/50th q. So I can just bring that down to my final line. So the slope of this line is 10 plus 1 over 50q. Well, down here, the slope was just 10, right? But in this case, because the slope is changing, we're going to have that variable still in it. So we're going to have this q. So as we move along, right, the curve, the slope of the curve is going to continuously increase as q goes up. So when q is, let's say, equal to 50, let's make that 50 just to make my life easy, right? I've got 1 over 50 times 50 is 1, and so I'd have 11, right? Sorry, the slope would be 11. And, I'd have to plug in 50 up here to actually get the total. So sorry, the slope is 11. So MC of 1 equals 10 plus 1 over, what did I say, 50, not 1, 50, then I get 10 plus 1 over 50 times 50, which is 1, so we get a slope of 11. At a slope of, let's say, or at a point, say, 200, right, MC of 200, I get 10 plus 1 over 50 times 200. So 1/50th of 200 is 200 over 50, which is 4. So I get 10 plus 4 is 14. So the slope is now 14 at 200. And then let's jump out to, say, 500. So the end marginal cost at 500 is 10 plus 1 over 50 times 500. Well, 1/50th of 500 is 10. So 10 plus 10 is 20. So the curve slope at 500 is 20. So the marginal cost at 50 is going to be 11. The marginal cost at 200 is going to be 14. The marginal cost at 500 is going to be 20. So what does that mean? So let's reiterate. What does the marginal cost mean? It means the cost of doing one more. So the cost of doing one more at 50 is going to be 11. The cost of doing one more at 200, so going from 50 to 51, going from 200 to 201, right, is going to be roughly 11, roughly 14, roughly 20. Okay. So that should give you enough baseline. We can practice one more. We'll do one more so that you can rehearse it. Okay, so let's do the 450 example. So total cost is 450,000 plus 500 Q plus 1/10 Q squared, right? All right, so what marginal cost, we're going to ignore the 450. That's just going to go away, right? So the 450 becomes 0. This we recognize that as q to the 1, so that becomes 1 times 500, right? And then we do q to the 1 minus 1, right? Becomes q to the 0, and q to the 0, right? Q to the 0 is 1. 1 times 1 times 500 is just 500. Okay, we're done with that. We bring down the 2. We bring down the constant. Then we bring down the q and the 2, right, the q squared, and we subtract 1, just like we did here a second ago. Well, that's 2 minus 1 is 1, so q to the 1 is just q. Okay, so we can just bring that down. 2 times 1/10 is 2 over 10, which is 1/5. Right? So that's it. It's that simple. I'll do one more, just make it up. Total cost is 2,000 plus 20Q plus 1/5 Q squared. Right? So marginal cost, we'll start working at, this becomes 0, right? 20Q is really Q to the 1, so Q to the 1 minus 1, right? So we'll bring down the 1, right? We bring down the 1, we bring down the 20, then we bring down the Q to the 1 minus 1 becomes Q to the 0. So one more line, we can ignore the 0. 1 times 20 is 20. Q to the 0 is 1, so 1 times 20 times 1 is 20. Right? Then we bring down, we look here, we say, okay, we'll bring down the 2, bring down the 1/5. Then I'm going to subtract 1 here, right? So I go Q to the 1/5, 2 times 1/5. I shouldn't have brought that all the way down. Sorry. 2 times 1/5 times Q to the 2 minus 1 is 1, Q to the 1. So we've got 2/5 Q, right? Because Q to the 1 is just Q. So 20 plus 2/5 Q. All right, that should give you enough information to go forward and do the quiz that I've just put on Canvas.